Good morning. I'll solve today a problem on jet propulsions. A turbojet engine having the following component performance cruise at a speed of Mach 0.8 at an altitude of 10,000 meters. The compression ratio is given as 9.0. Turbine inlet temperature is 1300 K. Isentropic efficiency of different components are given as: for compression, eta C is equal to 0.86. For turbine, eta T being 0.89. Intake eta I is equal to 0.93. For the propelling nozzle, eta J is equal to 0.95. Mechanical transmission efficiency, eta M, can be given as 0.99. Combustion pressure loss, del PB, is equal to 4% of compression delivery pressure. Calorific value of the fuel is 43,100 kilojoule per kg. Ambient condition at an altitude of 10,000 meters are 0.265 bar and 2 to 3 Kelvin. Evaluate the specific thrust and specific fuel combustion for the simple turbojet engine. I have illustrated here the schematic of a turbojet engine, and the operating principle has been illustrated in TS diagram, where the section A1 indicates the intake, followed by the compression and then combustion chamber, turbine, and finally the gas is expanded in the nozzle, producing thrust. With respect to operating principle, A01 is the ram effect in the intake. Then 01 to 02 is the compression of air in the compressor, where 01 to 02 is the corresponding isentropic compression. 02 to 03 is the heat addition in the combustion chamber with a pressure loss del PB. Similarly, 03 to 04 expansion of gas in the turbine, while 03 to 04 is corresponding isentropic expansion, and 04 to 5 indicate the expansion of the gas in the nozzle, producing the high velocity jet and thereby the thrust. And the corresponding isentropic expansion is represented here 04 to 5 Now look, the P5 would be either equal to the atmospheric pressure PA for unchoked condition, and for the choked condition P5 would be equal to PC, that is critical pressure. Furthermore, at the state point A, the PA being the atmospheric pressure, then I'll go to the solution methodology. Let me go to the next slides. Now, given PA atmospheric pressure as 0.265 bar, Ta equal to 223 Kelvin, and gamma of air as 1.4. Now we can evaluate sonic speed based on the atmospheric condition, that is A equal to root over gamma RT. Gamma is equal to 1.4, R 287, and temperature of air is 223. Thus, E is equal to 299.3 meter per second. After evaluating the sonic speed, I can calculate the speed of the craft CA as 0.8 into 299.3, because craft is flying at a Mach number of 0.8. Hence, the craft speed becomes 239.4 meter per second. Thus, I can evaluate CA squared by twice CP, considering CP is equal to 1005, and CA I have just evaluated. I got the value of CA squared divided by twice CP as 28.5 Kelvin. Thus, T01 is equal to TA plus CA squared by twice CP. Put all the values and you will get T01 as 25115 K. Now, for a given nozzle efficiency, I can now evaluate the ram effect, that is P01 by PA is equal to 1 plus eta I into Ca squared divided by twice Cp into Ta to the power gamma by gamma minus 1. Eta I is given as 0.93. Ca squared by twice Cp I have evaluated as 28.5. Ta 2 to 3. Gamma by gamma minus 1 becomes 3.5. Thus, after calculating this, I'll get P01 by PA is equal to 1.482. Thus, I can get P01, and the P01 I have got as 0.393 bar. So, after evaluating P01, I can calculate P02 as P02 by P01 into P01. P02 by P01 is nothing but compression pressure ratio, which is given as 9. So I have evaluated P02 as 3.537 bar. Now pressure ratio of the compressor is known. T01 I have calculated. Eta C, that is isentropic efficiency of the compressor, is given. So I can evaluate temperature rise of air within the compressor, that is T02 minus T01 is equal to T01 divided by eta C within the bracket P02 by P01 to the power gamma minus 1 by gamma minus 1. Put all the values. You will get T02 minus T01 as 255.43 Kelvin. Thus, I have calculated T02. So T02 is equal to 506.93 K. Now, for a turbojet engine, the turbine work would be just sufficient to run the compressor. So I can write Wt is equal to Wc divided by eta m. Eta m being the transmission efficiency. Hence, I can write Cpg into T03 minus T04 is equal to Cpa into T02 minus T01 divided by eta m. Now I know T02 minus T01. Eta m has been given as 0.99. When I put all this value, here I'll get T03 minus T04. So T03 minus T04 is here 255.87 Kelvin. Now T04 is equal to T03 minus 255.87. T03 is the maximum temperature of the cycle, which is given as 1300 Kelvin. Thus, I can evaluate it. I have evaluated T04 as 1044.13 Kelvin. I can assess now P03, pressure, total pressure at the state point 3. That would be equal to P02 into 1 minus del P by P02. This is the pressure loss in the combustion chamber, that is stated as 0.04. Hence, I have evaluated P03 as 3.396 bar. Now, eta T is the turbine efficiency, isentropic efficiency, can be stated as T03 minus T04, that is actual temperature drop divided by isentropic temperature drop. It should be T03 minus T04 dash. So thus, from the relation of eta T, I can evaluate T04 dash, that is isentropic temperature at the exit of the turbine, is equal to T03 minus 1 by eta T into T03 minus T04. I have evaluated T03 minus T04 as 255.87. T03 we know as 1300. Eta T is given as 0.89. So all values are known. Therefore, I have evaluated T02 dash as 1012.5 K. Now, look, I have evaluated P04 by P03 now by the isentropic relation as T04 dash divided by T03 to the power gamma by gamma minus 1. Thus, I have written P04 is equal to P03 within bracket T04 dash divided by T03 to the power gamma by gamma minus 1. Now here I know P03, I know both temperature T04 dash and T03. Thus I have evaluated P04. P04 is becoming 1.2496 bar. Thus, the nozzle pressure ratio is P04 by PA. That is becoming P04 is 1.2496. PA atmospheric pressure is equal to 0.265. So this ratio P04 by PA is now 4.716. Now let me assess the critical pressure ratio, which is equal to P04 by PC. That can be expressed as, I have proved the relation, 1 divided by within bracket 1 minus 1 by eta j within bracket gamma minus 1 divided by gamma plus 1 to the power gamma by gamma minus 1. Now, put the value of eta j as 0.95. Put the value of gamma here, that is equal to 1.333. Now I have put all the values with eta j as 0.95. I have got P04 by PC is equal to 1.914. Hence, P04 by PA is greater than P04 by PC. Thus the nozzle is choked here. So here the case we have arrived, here the atmospheric pressure is less than the critical pressure. Now we can say in this case when the nozzle is choked, T5 must be equal to Tc. That would be equal to 2 divided by gamma plus 1 into T04. So I know T04. T04 is equal to 1044.13. Gamma I use 1.33. Just I have evaluated T5. T5 is equal to 895.1 K. Now P5 would be equal to PC, and that would be equal to P04 into 1 by P04 into PC. The ratio of P04 by PC I have evaluated as 1.914 and P04 as 1.2496. Thus I have calculated P5 as 0.653. Thus rho 5 is equal to PC divided by R into TC. I know PC, I know TC, the R is equal to 287. So I have put here all the values and I have got rho C as 0.254 kg per meter cube. Now C5 is equal to root over gamma R into TC. I know TC as 895.1. I know the value of gamma as 1.333. R is equal to 287. Thus I have calculated C5, which will be here 585.2 meter per second. Thus mass flow rate can be evaluated as rho 5 C5 into A5. A5 is the effective area of the nozzle. Thus A5 divided by M can be written as 1 by rho 5 into C5. I have put the values of rho 5 and C5. Thus I have assessed A5 by M as 6.728 into 10 to the power minus 3 meter square second per kg. Thus the specific thrust is evaluated now. Ts is equal to C5 minus Ca, which is the momentum thrust, plus the pressure thrust, plus A5 by M into Pc minus Pa. Pc is the critical pressure and Pa is the atmospheric pressure. I know all the values, C5, Ca, Pc, Pa, and A5 by M I have just evaluated. Thus, when you do this numerical calculation, you will get 606.85 Newton second per kg. Thus, I have got the specific thrust now. That is 606.85 Newton second per kg. Now, heat added, that is Q is equal to Cpg into T03 minus T02. I know T03 as 1300 and T02 as 506.93. Cpg I have used as 1.148. Thus I have calculated Q as 910.44 kilojoule per kg. Now let us consider m dot A be the mass flow rate of air in kg per second and m dot F be the mass flow rate of fuel in kg per second, then by energy balance we'll get m dot F into del H is equal to m dot A plus m dot F into Q, where del H is the calorific value of the fuel and Q be the heat added in the combustion chamber. And from this equation I can project the value of m dot A by m dot F, which is equal to 1 by F, where small f be the fuel air ratio, which can be written as now del H by Q minus 1. Now del H is known as 43,100 and Q I have evaluated as 910.44. Thus I can calculate m dot A by m dot F as 46.34. Now inverse of 46.34 will give the fuel air ratio, thus F is equal to 0.0216. Now from this fuel air ratio, I can calculate specific fuel consumption. Thus a specific fuel consumption is equal to 3600 into F divided by Ts, that is the specific thrust. I have already calculated specific thrust as 606.85 and fuel air ratio as 0.0216. Thus specific fuel consumption becomes 0.128. Hence the answers are the specific thrust is 606.85 newton second per kg and specific fuel consumption of the turbojet engine is 0.128 kg per kilowatt per hour. I have solved here a problem on turbojet engine with details. Hope you will be able to solve similar problem on jet engine. Thank you for listening.